Okay, maybe we'll begin now with the second talk. It's a pleasure to have Adrien Brochier. He's going to tell us about quantization of character varieties, topological field theories, and the Riemann-Hilbert course.
Yeah, that's a very long name. Thank you. First of all, of course, I would like to thank the organizer for inviting me on organizing this very, very cool conference. And I must say, I don't think I've ever felt somehow so comfortable giving a talk, because many of the pieces I'm going to use in this story somehow have been already explained by other people, either yesterday or this morning or last week in the summer school, probably much better than I would have. So it's very enjoyable. I basically just have to sort of put the pieces together and try to explain some application of that. So I'm basically going to try and give you some overview on quantization of character varieties, which are things that many of you already know, but I will define them in a second. And then in particular, I want to explain some joint work with Ben-Zvi, David Jordan, and Noah Snyder, where we sort of unify those different approach, and we, perhaps more importantly, we put them in the framework of topological field theories. So the sort of rough plan is as follows. I sort of want to remind you various point of view on the representation category of quantum groups. So there are various ways to describe this category, and they are all interesting for various reasons. And I will try to convince you that somehow all this point of view has something to do with the character variety of the disk, and that somehow they all, or at least almost all, have some natural extension to arbitrary surfaces. And in fact, one of this point of view does not quite fit into this picture, and if I have time, which I might not, I will try to convince you that's because somehow they are on the other side of the Riemann-Hilbert correspondence. So let's start from, I want to say, the defining definition. So like everybody on Sam just before, let G be your favorite reductive or simple complex algebraic group, and choose some complex parameter, and to be on the safe side, Q will be generic. And in fact, you can really safely assume that G is SL2. In fact, I will often do so myself somehow. So to that, we can attach an interesting category, RubQG, which is a category of infinite level, or if you prefer, locally finite dimensional, modulo over the quantum group. So this is some sort of Q deformation of the representation category of G. And as mere category, this is really just the same thing, but the main difference has, as you know, of course, a different tensor product, and it has an interesting monodromy category structure. And in fact, it's even a Riemann category, and as a consequence, you get representation of bed groups, and interesting not invariant, which generalize to the Jones polynomial. Of course, you know that, I suppose, but somehow the point I want to make is that those invariant in terms somehow determine this monodromy category in various ways. So one of them comes from scaling theory, and Sam already mentioned that this morning. So somehow in the case of SL2, in an appropriate sense, every map between tensor power of the defining representation are actually images of some tangles. So tangles give you morphism in that category, and in a way, all of them are this form. And in turn, they are determined by the value of curve on cap. So there's something a bit special here, but that's not really a big deal. Well, you won't think about the defining representation as being self-dual, but that's not very important. But anyway, you can, so basically you can simplify every crossing using this Kaufman scale relation. Also you can express everything in terms of identity morphism on just this curve on cap. And so you can just define a category as having object finite sequence of points, or whether sequence of points on the disk. And as morphism you take this tangles modulo the relation. And so then it's well known that the fundamental representation of SL2 sort of generates the whole category under tensor product. So this sort of folklore theorem, and there is this very funny paper by Peter Tingley, funny in a good way, there's this funny title, which sort of explains how to do this carefully, which say that the representation category of RubQSL2 is some sort of completion of this category, which I call the topological category. Now there is perhaps my favorite description of this representation category, and we also heard about it yesterday in Nina's talk. So there is a construction coming from conformal theory, and if you're not theorist, you might know this as the concept integral, or perhaps as some perturbative expansion of Chern-Simon theory. And the idea is you define this rub KZ category as being just rub G, but this time with the same tensor product. Sorry. And then there is some fairly complicated but natural way to define an action of the braid group on this category using some differential equation defined on the configuration space of points. So it's called the Knieznik topological equation. So this is what KZ means. So this is an analytic construction, so it's highly transcendental, it's very non-explicit, and there is some sort of small miracle happening that you can actually encode that into some braid monadal structure, which is itself very non-explicit. But somehow the the good point is that it's very, very geometric and it's very natural of all this construction. Thank you. Of all those constructions, somehow that the only one which is not ad hoc in a way. So in my mind, this is really the of course I should say that the thing that the result you get, this famous theorem by Kohno-Drinfeld and Kasdas mostly, is the same as RubQG. And for me, this is really maybe not the, but at least one of the best explanations of why quantum groups exist at all, actually. And then there is another point of view, which is, well, why quantum groups are quantum, so how do you think as RubQG as some sort of quantization? So the idea is that RubG is a symmetric monadal category, so it's a commutative algebra, and RubQG is not so commutative, so what you want to do is this difference exactly tells you how far RubQG is from being symmetric. So you get, you plug Q equals 1 plus H bar and you expand, and you get a power series in H bar without a constant term. Okay. And so you take the first element, you want to call this the quasi-classical limit of RubQG. And it turns out that this element is nothing but the canonical element that associated with the tuning form. And for why people call this structure an infinitesimal braid monoidal category, and of course there is sort of some sort of analogy with the formation continuation of Poisson structure. But it turns out this analogy can be made rigorous. And the idea is that this category of G is really naturally identified with quasi-coherent sheaf on this classifying stack of G. So you should think of this as some sort of categorified algebra function. So here, of course, this thing you should think about it as a stack. Otherwise, taking the equation by G is just some really boring operation. So I'm really saying basically that just instead of identifying things which are in the same orbit, which in that case would be really nothing, I want to work G equivalently. So I want G equivalent vector spaces, which is representation of G. And the idea is that this element T to G is a so-called two-shifted symplectic stack, which some of you learned about in Pavel Safronov's lecture last week. So I'm sure you mentioned this example. This is one of the main ones. So there is this RubQG is really a quantization of something Poisson, basically. And from that perspective, this KZ category I was talking about just before, if you know what that means, fine. If you don't bother too much about that, but really it coincides with the quantization you get from the so-called formality of the little disk operator. Anyway, so now I want to sort of extend those different point of view to arbitrary surfaces. So let S be any topological surface. So what I want to call the representation variety of S is just the space of all representation of the fundamental group into G. And the character variety is a quotient of that by the adjoint action of G. Now I should really say the character stack because this will be really an important point that I'm actually thinking about stack. So a very important theorem which has been proved by Atiyah Bott-Goldman for the underlying variety, and there is a more recent and much more technical version by again Fontaine-Nicolas back here on the literacy, which says that this character variety or character stack carries a canonical Poisson structure. And here by canonical I mean that it's really defined entirely in terms of the topology of the surface. So in particular it's a diffeomorphism invariant. And in fact, not that it matters that much for now, but it's actually a better invariant than the fundamental group. So it really depends on the surface. So for example, like pair of points and punctured torus will have different structure in general. Yeah.
So you mentioned on the previous slide that the shifted symplectic structure on VG is something like very easy to write to C in terms of the category. Is this symplectic Poisson structure something that we can like see in terms of the category of sheaves? Is it somehow like?
I don't think so. There is this funny thing that somehow two shifted family history are in a way much easier or much less complicated at least than 1 and 0. Yeah, I definitely. I mean, yeah. There is some construction I will talk about in a moment.
Is it just some differential form you can write on anytime machine and then you can?
Yeah, I mean, there is some sort of finite dimensional non-canonical construction I want to mention, but I sort of assume your question was about the sort of PTVV construction.
Well, I mean, like we heard in the last lecture all about kind of categories deforming these varieties.
Yeah.
And so.
Yeah, I mean that I will definitely explain, but somehow it's the nice thing. This PTVV construction is really canonical, and this one is very complicated. And I was about to say that. Well, I'm going to say that in a minute. And then there is some sort of combinatorial version which is much easier on that. I will explain that.
So what do you mean by really depends on the surface?
Well, I mean that, for example, like the pair of pounds on punctured torus, they have the same character variety because they have the same pi 1.
Oh,
But they have
they're
different.
not homeomorphic.
Yeah, that precisely. But the character variety do not know that, but the Poisson structure does. So the sort of basic but very, very important observation is that if you take this character stack of the disk, of course, if we are taking the character variety, it would be completely trivial. But if we take the character stack of the disk, then we recover this classifying stack. So the sort of informal idea is that character variety of arbitrary surfaces are obtained by gluing together shields on that, which again is just rub G. And so of course this is very non-true if you take algebra of global functions. So if you take the underlying variety instead of stack. So here this is really somehow crucial. And the sort of precise formulation of this fact that you can get character variety of surfaces by gluing together character varieties of disk is a theorem by Ben-Zvi, Francis, and Snyder, which say that the thing that to a surface attach quasi-column shield on the character stack is the sort of top-dimensional part of a two-dimensional field theory. So this is sort of a neat way to express how it has nice behavior on the cutting and pasting operation. And so in general, this Poisson structure is given by, I put code, integrating the killing form. So in Atiyah Bott picture, this is like literally true. In this PTVV formalism, this is some sort of formal / derived algebraic form of integration, which is a very complicated thing. But the idea is that this Poisson two-shifted structure on BG is actually what determines this Poisson structure on character varieties. So in particular, we also, this gluing operation has some sort of a nice behavior for the Poisson structure as well. So we have a fairly simple recipe for its behavior under gluing. And the sort of precise version of that is due to Pavel Safronov, and there is some similar idea in a paper by Kalak. And this is all very much inspired by some other paper in a different language by Alexei F. Malkin and Meinrichen. And the sort of general idea is that gluing corresponds to some version of Hamiltonian reduction. So I call this a slot on another theorem because, of course, there are different ways you can glue surfaces together. And the sort of general idea is that there are moment maps on Hamiltonian reduction, some sort of stuff, and that you can build character varieties of surfaces out of that. Somehow one important example is that if you have a punctured surface and you want to glue back a disk to get a closed surface, then the monodromy around the puncture will give you a moment map. And gluing this mask, in that case, is literally Hamiltonian reduction. And this is an important example. And then gluing surfaces together, it can express using some form of Hamiltonian reduction as well. So to give some example, there is some sort of general philosophy that told that everything is easier for punctured surfaces. So let's assume that for now. So in that case, the fundamental group of course is free. And so if you choose generator, you get some non-canonical identification with just a bunch of copy of G. Like you just choose one element of G for each generator. And in particular, it implies that it's a priori complicated category of quasi-coherent sheet, and Sam already said something like that a few minutes before. It's really just modules for the algebra on the representation variety, but now you just work G equivalent. You want a G structure on this module, and you want everything to be compatible. And so there is a famous construction in the 90s by Fort and Rossley, which says that this canonical Poisson structure on the character variety actually leads to a non-canonical, in the sense that it will depend on this decomposition, Poisson structure on the representation variety. And this one has a fairly explicit combinatorial expression using classical R matrices, if that answers your question. And so sort of two building blocks example are the representation variety of the annulus. In that case, you get just one copy of G. And you get some Poisson structure that was discovered a long time ago by Semenov, James, and Steve. And as Sam said, for the puncture torus, you just have two copies of G. And so you get something that people call the Heisenberg double. And you should think of this as some multiplicative version of the cotangent bundle. Yeah?
Do for controls have to have something like punctured marked boundary?
Say again?
Do for controls have to have something like marked the boundary for their construction?
Yeah, I mean, yeah, it depends on more than just this identification.
It also depends on the composition, not only on the choice of the boundary.
I'm sorry?
It also depends on the composition, not only on the choice of the boundary.
Yeah. I mean, if it depended just on this quantization, then it would contradict what I said before, that the Poisson structure depends on more than the pi one. So you need some what they can call ciliated graph. So it's some sort of ribbon graph decomposition of this surface with some cyclic ordering at the vertices. And even that, there are like some non-canonical choice, but they somehow all disappear when you take the question. Anyway, so yeah, Sam already explained very well how this thing is somehow like degenerate to the quaternary bundle of capital G on little g. And then for other surfaces, you have this procedure like doing along pair of bands basically, and for closed surface, you do Hamiltonian reduction. So this somehow has a quantum version, which is also fairly old, like from the 90s, which I want to call the combinatorial quantization. So this GSTS Poisson structure quantized to some version of quantum version of algebra on G. This is a fairly well-known algebra which has been discovered in many different contexts, and it's called either Bray dual, the reflection equation algebra, or some other name. As far as I know, it's been discovered by Majid and Donny Woodruff, but it's been considered by many people. And in particular, it's important in equivalent quantization, like G equivalent quantization. And in particular, it's a natural framework to quantize conjugative classes of G, which is will be interesting later. So as Sam already explained, this Heisenberg double quantized to DQG, and that's very nice because I don't have to explain to you why this is such an interesting algebra. He already convinced you of that, I'm sure. And so for arbitrary punctured surface, you just put like G copies of DQG on n-1 copy of QG, and you cancel that together using this so-called braided transfer product, because you want to do that sort of internally to grab QG. And then to get the quantization, so this gives the quantization of the representation variety. And then if you want the quantization of the character variety, you just take invariant. And here I really mean like algebra of global functions. So one nice thing about this is that it's very explicit, very algebraic. But of course, it depends a priori on the combinatorial decomposition of the surface. And all the sort of topological features that this Poisson structure had, in that case, you have to prove them by hand. And another thing which is annoying, it's originally not defined for closed surfaces. So you might say, well, you just need some sort of quantum group version of Hamiltonian reduction. And we've known something like that for a while, but it kind of works only formally. And the sort of correct version of that is appeared only recently in the literature. I think it's due to Vasco Varangelo. I don't know if it appears before that. In either way, it's very recent and fairly subtle. To my knowledge, like Pavel Safonov wrote a paper recently, and this is the first one where I actually work out the fact that it really quantize the sort of Hamiltonian reduction we want. So this part is really not obvious. Then as Sam also already explained, we have another quantization scheme using scale theory. So if I have a 3 manifold, I can look at the vector space of isotopic classes of links, or as I mentioned during this talk, really you should think of, for general G, you should take another trivalent graph, something like that. Modulo the scale relation, so either the one corresponding to G or the Kaufman one if you're in SL2. And this construction is sort of obviously functorial with respect to embeddings of manifolds. And in particular, if you have a surface and you cross it with an interval, because it's functorial with respect to embedding, or if you prefer because you can sort of stack along the interval direction, then you get an algebra. And again, this is some sort of well-known but not completely straightforward fact that this is a quantization of the character variety. Here I should probably have brush on genus as well. So a good feature of this construction is that it's very elementary in a way, at least to define, and it's obviously topological, so it carries mapping class with action on anything you want. The thing that it's very difficult to handle algebraically. So already for SL2 there are a lot of very, very technical hard results about the sort of structure on this. I mean the main example is this finite dimensional equation, which is pretty difficult for 3 manifold, I mean. And another thing that also they are defined in a purely topological way, they are not compatible in any way with gluing. Like there is no TFT or gluing formula around a priori. And somehow one motivation of this talk is to explain that in fact that can be improved. Anyway, so long story short, what we really want, because we are greedy, we want the best of both worlds, and actually we want more. We want everything. What we want is an actual TFT with some nice gluing formula, something which is defined in a purely topological way. But then we want an explicit computational, combinatorial way to compute it, and we want it to have like some clear relationship with representation theory. So the sort of idea underlying my work with David and David is to use this formalism of factorization homology that Claudia and Hiro told you about before, to quantize the category of fields on the character variety directly rather than the attribute of global function. Because this is the thing that behaves well on the interface. So recall again from Claudia's talk or from Hiro's lecture that we want to consider the category with which I call MFLD2, which has object-oriented topological surfaces. Morphisms are smooth embeddings between them. And then I want to add two morphisms, which are isotopies between those. And usually people keep going on, but I don't need that, so you can just forget about it, or more precisely, you model it by the higher isotopies. And it has a symmetric modular structure, which comes from disjoint union. And then I call disk 2 the full subcategory of finite disjoint union of disks. So the sort of basic idea is that it provides you with a, you should think of it as some sort of coordinate-free description of red tensor category or Riemann category, as opposed to this usual axiomatic or generator modulation definition. So Riemann category determines only more or less the same, up to some technicalities, as a symmetric monoidal functor from this category to some category of linear categories. It's a sort of like Lurie style definition of an algebra with a little two-disk operad or two operad. So the basic idea is that to a single disk you attach A, and because it's symmetric monoidal to a bunch of disks, you just attach tensor product of bunch copies of A. Then to the embedding of two disks into a bigger disk, you just get the multiplication on A, so the tensor product. And then you can sort of switch those two disks inside the bigger disk because we're in 2 dimensions, and this gives you an isomorphism because the 2 different ways of multiplying X and Y, and this is just the gradient. So I'm sure many of you already saw this picture before. So very important theorem by Ayala Francis and Tanaka is that the symmetric monoidal functor, which is determined by some Riemann category, has a canonical extension to the category of all manifolds. So the fact that this thing exists is just some abstract nonsense, but then there is something much better, which is somehow an algebraic characterization of this functor, which they call excision, and I will tell you what it is in a minute. So again, I think Claudia explained that yesterday. if your surface happen to be a one manifold across an interval, then for some about the same reason as for skein algebra, but just one dimension below, those things will be algebras, which in that case means monoidal categories. So again, that's because it's functorial with respect to embedding, or because you can sort of, if you take an annulus, you can just stack them together and it gives you.
May I ask you to slow down a little bit? What is the integral of S of A? Just repeat the previous transparency.
Sorry, yeah, I should have pointed that out. That's how I call this extension.
So what is it? Just integral, so some symbolic integral is not exactly integral.
No, it's not an integral, it's really a notation. So the idea is that a ribbon category gives you a functor from that to that. And the sort of...
And the dash means surface, right?
This means disk, and that means arbitrary surfaces. And the idea is that there is some very formal way to extend from here to here, which you sort of think morally as a way to like cover your surfaces by many disks, which is why we use this sort of integral sign. And somehow what I want to give now is like an algebraic sort of concrete recipe to tell you how it's computed. So yeah, so if you have some cylinder or some one manifold across an interval, you can stack them together and get an algebra. And if you have a boundary, then factorization homology of that will be a module for that. So for example, so here this guy will give an algebra by stacking together. And here I can take the disjoint union of that, and embed them into a larger functor torus, and this gives me a map from that onto that to that, just by functoriality. And this satisfies the axiom sort of categorical version, of a module of an algebra. And now if I have another surface with a circle boundary, this will be, say, so this guy will be a left module, and think of it as a right module. And the basic idea is that when I glue them together, algebraically it just boils down to taking the relative tensor product of this algebra. So all of that is working with categories, so it might seem fairly abstract, but really it's just, I mean, we have a nice notion of what an algebra is and what a module is, and we should think of it as a sort of straightforward categorification of the notion of relative tensor product here.
You switch the role of the surface of the category and X.
That's true. Yeah, I apologize for that. Sorry, yeah, there should be X here. This whole thing should be here on the H here, and then X. Yeah. Actually, I had it wrong all the way, and I noticed it, but somehow I forgot to change it. Yeah, sorry.
You just wanted to emphasize that it's a functor of both the category and
That's true. Yeah, sorry, so the way it's written is wrong, but basically the idea is that like gluing things together is taking relative tensor product of modules of an algebra. So this is sort of as simple as it can get, and it's sort of just a natural extension of the fact that disjoint union, which is gluing over nothing, goes to tensor product, so gluing over something goes to some relative version of the tensor product. Anyway, so here's time to state our main results. So this is David Ben-Zvi and David Jordan, as I mentioned before. So the idea is that we have this category which is completely canonically but abstractly defined, and we also have this quantization with this thing that I call moduli algebras due to Alexeyev, which a priori depend on some decomposition. And the sort of general theorem is that if you pick some decomposition of a punctured surface, then this gives you an identification between those two quantizations. And here I really want to emphasize something, so you might look at that and say, well, then, you know, what's new? We already use that, and in a way it's much simpler than this abstract definition. But what's important here is that we get those algebras as the output of some purely topological machine. So we don't like define them by generator and relation. We have something which is defined topologically, and then we rediscover those algebras really the result of some computation, basically. And we give some sort of algorithm, some machine that rediscovers algebra. And another nice thing that actually works for any Riemann category. There is nothing special about OFPG in that case. So this is a statement for punctured surface, and as I said before, closed surfaces are usually more complicated, but we have a second, this is basically the main result of our first paper. We have a second paper where we do the case of closed surfaces on surfaces with mark points. and we sort of developed a categorical machinery which is sort of mimicking this stacky version of Hamiltonian reduction, whatever, and we have some explicit description of that. And in particular, as Sam mentioned, for the closed torus, we get some category of equivalent DQG module, and if you add some marked point on your torus with some marked by some appropriate conjugacy class, you get some variant of this category. And a very nice feature of this category is that, again, Sam mentioned that taking global section, or if you want, if you do the affine version of Hamiltonian reduction instead of the stacky one, then you get the spherical double affine equialgebra. And you really get it with both parameters. So the Q parameter is that one, and the T parameter depends on this marking on the torus. And because everything inside is completely topological, you get this SLT action, which is a mapping group of the torus for free. So this is very nice. And as you might guess, I was pretty excited when I saw Sergey's talk, because he sort of started with something pretty similar and include, and it feels like this should be a nice framework for constructing his invariant. I mean, so I hope that is.
You see, the high is with one function. No, you cannot make any number of functions here, right?
Say again?
1 or 4. The high is with one function.
Yeah,
Your T2 with one function divided by the symmetry, by symmetry. This is that's different, right?
Yeah,
the high is already here. Already. Before the last line, the high is already here.
I'm sorry, I don't.
Minus 1 point, your T2 minus 1 point divided by S2, and you take orbifold phi 1 and character variety. This is the high.
I mean, I take the character.
Anyway, you are not free to make any number of functions. This is,
I'm completely free to make any. Yeah, I can choose any number of functions. I'm just not sure what we get in that case. I'm sure. In that case, I have a puncture torus with one point marking by this Calgero conjugacy class. Yeah. I actually look at the stack, which is why I get this more complicated category, and somehow the optimization of that is a spherical down.
What's the meaning of marked point?
So basically, you have a version of character like the variety version is that you can, if you have a surface with boundary, you can restrict to other representation where the monodromy around some boundary belongs to some conjugacy class. And it turned out that those things are somehow so the character varieties are Poisson, and those things are like the simplicities of that. So that naturally shows that one can.
Marked points means there is an untrivial one that's coming out.
Yeah. I mean, if you choose a trivial conjugacy class, it's like not having a marked point at all. So in that case, you just have a cluster.
Can I just make a remark?
Sure.
Ivan, in the case of T2 modulo Z2 action, so you have 4 mark points. The
C61.
C61
is a story about 4 points.
Yes, I'm not asking you a question, I'm telling you something. Ivan, I'm explaining that there's a version that was developed by my PhD student Tim Wielink, which gives you the C-check C story.
Yeah, that's
This
4
is
points,
type.
but no greater than 4, because we
right.
have only C-check C1.
That's right.
Not exactly as you say, you are not free to choose any number of marked points here, right? To preserve integrability, you need to be absolutely exact here. Right?
Anyway, so yeah, this is one of nice consequence of this formalism. We get this sort of topological construction of the spherical large. And so if you don't really see what I mean by a combinatorial decomposition, here's an example. So if you start with a punctured torus, you can sort of stretch it. Look at it as being obtained by giving some what I want to call flat handles on a disk. And somehow we have a recipe which says that each of these handles is given a copy of OQG, and then somehow for every every copy of OQG is a subalgebra, and for every pair of handles, whether or not they interact or not, we have some bread diagram that tell you the cross relation. So everything is very, very explicit and very combinatorial. That's really not just some abstract nonsense.
I have a question.
Yeah.
So the very slides back when you had the in Atiyah, you had there was n marked points. You had n minus 1 tensor copies of OQG.
Yeah.
And so is that, but here, is that related to this and the way you're attaching the flat handles and why it would be minus 1 there?
Yeah, the thing that that might not be. Yeah, thanks for asking that. So the thing that I said that I had like G copy of DQG, But in fact, DQG this is a construction of DQG. DQG as an object is 2 copies of OQG with some cross relation.
But then you also had for the punctures extra OQG.
Yeah, but I have n minus 1.
So you had -1, yeah.
So in that case, I have only 1 puncture, so I have DQG tensor mapping.
I might have to ask you then later with the pictures. I'm not getting it yet.
Like there is yeah. Like the number of copy of OQG in total is the number of generators of the fundamental group. So it's 2G plus n minus 1.
Okay.
Yeah, I remember that getting confused. So at some point I was giving a talk about that, and someone asked me, well, for the puncture disk, then there is only like 1 puncture, so it doesn't work. And it took me 1 hour to remember that it was actually just 3 and minus 2. I was very, very confused by that. I think the guy asking was Felder, so I was maybe a bit impressed. Anyway. So he should have remembered that too, to be honest. But anyway. So as Sam also already mentioned, and I got all the credit right. So there is a scale version of that, which is due to Juliet Hood and Theo Jonathan Fred. As you say, all of that is sort of foreseen by Kevin Walker in the 90s, except he didn't really have this sort of categorical language available at that time. And so just as RobQG can be thought of as some appropriate completion of the scaling category of the disk, then factorization homology is completion of the scaling category of the surface. We have just look at finite collection of points on your surfaces on tangles between them modulo the scale relation. So in particular in that category, the endomorphism of the empty collection is scale algebra. And so this gives you basically this tells you that the 2 approaches to quantizing like global function and character varieties actually are isomorphic. And in particular, it tells you that all those well, the result before also tells you that all these combinatorial quantization are sort of isomorphic to each other, which wasn't obvious known, I think. And the other thing that it really tells you that scaling categories satisfy excision, which is definitely not true for scaling algebra. And again, this is really because scaling categories are sort of analog of category sheaves, while scaling algebra are analog of global function. And then I will only mention it briefly because this will be a big part of Noah's talk on Thursday, I think. If M is a 3-manifold, then of course you can also define the character variety exactly the same way. And there is a map that way given by restricting it on the boundary. And this is Lagrangian. And because we are working with sort of stacky version here, Lagrangian is really an additional structure. I'm sure Pavel told you everything about this as well. And there is also another slogan which tells you that bluing somehow corresponds to Lagrangian intersection. And Pavel in this paper also has a very nice formalism that explains that. And it turns out that this construction of factorization homology, which gives you, I'm not sure I said it out loud, but it gives you a 2-dimensional TFT, it actually extends to a dimension 3, where you get sort of vector spaces for closed manifold, unlike functors between those categories for 3-manifold with boundary. In particular, for combining with Juliet's result, for closed 3-manifold, we recover scale modules, and for manifold with boundary, we get this relative version that Sam was talking about. And of course, there is a particularly interesting situation is when you take the complement in S3 of a knot, so you get some 3-manifold with boundaries of torus, so you get a map like this. The sort of classical variety underlying that guy is a very interesting and very complicated knot invariant, which is called the A polynomial for G equal Sn2. Anyway, or rather the sort of image of this map is that invariant. And so basically we have some sort of canonical scheme that quantizes this construction and gives you an object in this category which is closely related to the spherical Daha. There is, I don't know, a lot of works, most of which I don't really understand, to be honest, which sort of aim at connecting like representation theory of the spherical Daha with various well-known knot invariant, and it seems that it's a nice framework to sort of do that. Okay.
Can you explain why spherical Daha arises? Because you don't have any punctures on that part.
Well, no, you're right. I mean, in that picture, that would be an Atiyah Bott-Goldman. I'm not entirely sure we should proceed. Like it's not really good work for the math, and it's not for every node. For some special class for some not parameterized nodes, there might be a way to put some marking back and get module for the arbitrary.
You see, the problem is that Qt scale is not well defined, but a spherical Daha is supposed to be Qt scale, but
That's
it's not
the same
local.
sort of
There's some
approach,
good
yeah.
example by Adrien Brochier that is not exactly local. So, of course, spherical Daha is Qt scale, but this is not true because there's no local
I think
definition.
there are some.
Just to explain
some
to
things
respond
about
to me a question about Qt, there is only one Qt here, no, not Qt.
In that case, definitely, yeah. Yeah, I don't want to say anything. Yeah. So that was the sort of story on the. Oh, but I still have 15 minutes left. But crazy. So I can try to tell you a little bit about Riemann-Hilbert, so it's more dangerous. It's really some work in progress, so I apologize if that's kind of vague, but I told you before that my sort of favorite construction of this category of quantum room is coming from this KZ equation. I like it because it's very sort of natural and geometric, and I will try to convince you that there is an analog on the for arbitrary surface, but that somehow it's on the other side of the Riemann-Hilbert correspondence. So if you start with a Riemann surface and you take some collection of points on it, say none on T to be on the safe side, and you can consider the moduli space of meromorphic connection of this surface with some like sufficiently regular singularity at each point. And the Riemann-Hilbert correspondence tells you that there is some analytic isomorphism between the moduli space, or maybe moduli stack of those connections, and the character variety of the surface you get by taking the underlying topological surface of C and just removing a disk around each function. So this thing is really analytic, but you can turn it into something almost algebraic by taking some formal completion. So on this side, you take the formal neighborhood of like the trivial representation. On here, the formal neighborhood of the trivial connection. And if you do that, it turns out that the left-hand side, so exactly as like the character variety is just a bunch copy of G, in that case, mod out by G again. And somehow this side will be a bunch of copy of little g, mod out by some gauge transformation. But somehow, if you like sufficiently close to the trivial connection, really you're just modding out by G. And basically, if you were on a puncture disk, this Riemann-Hilbert correspondence would morally be the exponential map, modulo issues. So it turns out that the sort of the bread group of this underlying topological of the surface of underlying C, it acts on this moduli space by something called monodromy. So basically, the idea is that you've chosen a bunch of marked points, and somehow, if you pick your favorite connection, which has regular singularity as a marked point, you can move the marked point just a little bit, and there is a unique way to pick a new connection on this new Riemann surface, which has the same monodromy as the one you had before. So there is something a little bit funny that happens, which is that you can take the moduli space of Riemann surfaces with a fixed number of marked points, and you have some sort of, I don't know, like bundle or sheaf or categorical sheaf over that, where the sort of generic fiber is a moduli, not generic, like the fiber is a moduli stack of meromorphic regular connection on that, and this thing has a flat connection, which connect the fiber with where you move the points. So this is, I don't know, sort of weird phenomena. But anyway, in that way you get some action of the bread group, which has some analytic description. And you have another action on this character variety just by moving the boundary component. And so recall this standard fact that G star has a Poisson structure that comes from the bracket. I suppose this is well known, and as Sam also mentioned, using the killing form you can sort of identify those. So particularly we get Poisson structure on that, and we get a symplectic structure on that, which comes from the canonical symplectic structure on T star G. And there is some, I don't know, theorem. I don't think it's actually written that way anywhere in the literature, but there are like bits and pieces everywhere. So some version is also due to the Alexeyev, Malkin, and Myroken, and then there are results due to Bolt, Etching, Reference, Naif, Simpson, and probably many others. Which tells you, first of all, that the Riemann-Hilbert correspondence is equivalent with respect to the action of the Bragg group. And there's this funny thing that, so this Atiyah Bott-Poisson structure, it's very complicated, it's very non-linear in some way. But if you identify the moduli space of flat connection with that, which is somehow, as far as Poisson manifold are concerned, it's like as simple as you can get, it's just a bunch of cotangent bundle and a bunch of linear Poisson structure. But in fact, then the Riemann-Hilbert correspondence becomes Poisson when you do this identification. So there is this funny thing that is very complicated Atiyah Bott structure, at least formally, it's isomorphic to a much simpler one.
What is the Poisson structure on n copies of G?
This just comes from, this is really just the product of the linear structure. Hmm? It's the KK, the Curry of Poisson structure. I guess people call it the linear Poisson structure. It's really just the bracket of G.
Okay, yeah.
Just a question. So the braid group, it is not true that the braid group will let only on G to n minus 1 component. It will involve everything, right? What is the problem with the right hand side when you calculate explicitly the action of the braid group? In the left hand side, by definition, right? If you explain, right?
Yeah. No, I mean,
the right hand side.
No, here,
it's supposed to act because of the functions,
this is not the Riemann. Here on both sides are flat connections.
But you mentioned it is specifically about the action of braid group. So what is the problem with calculating the braid group in the right hand side? It will be not Gn, n minus 1 is the number of functions. N is the number of functions.
I don't think I said there was a problem. Like there is an action.
Group,
there is an action of the braid group on that.
Yes, by definition, by
and you can like just transport it on that.
And what? It will be only G and n minus 1 component, or much more sophisticated. So
I'm sorry, I don't know.
Did I catch correctly that there are some problems calculating the action of braid group explicitly with the right hand side? Maybe I was wrong.
Group, you mean the diffeomorphism?
I don't know, like
whole surface.
Not generalizes.
With the left hand side is by construction, by definition.
Yeah.
With the right hand side, it can be.
Oh, you mean like sort of writing down the full value?
I mean explicitly with the action, not exactly with the link.
No, I think that's pretty easy to write. As I said, like this thing is some sort of like finite dimensional description of the moduli space of flat connection. On this action of the Bragg group, it comes from, I don't know, like for the punctured sphere, it's called the Schlesinger equation, so it's some differential equation.
Small n is the number of functions, right? Small n, right?
I mean, it depends what you mean by description. Like there is, as I said, it itself comes from a flat connection, and you can write it explicitly. So there is a differential system whose monodromy gives you the action on the space of flat connection. It's a bit weird. Then, of course, you get something which is analytic, so it's not explicit, but somehow my point is to, in a way, the whole point of that is to compute it. I should have said that. Anyways. So now there is this nice thing that the KZ equation I was mentioning before, it has a sort of natural analog for any surface, and in fact it turned out that factorization homology was very much inspired by conformal field theory on this formalism, so it's natural to expect that they are related somehow. So the B here is for Bernard, so it's clinic symmetric of Bernard. And so you get some monodromy representation of the Bragg group of your Riemann surface for an S of G transfer to the M G invariant for any finite dimensional module. And I don't really call this a theorem because I don't think it's known in general. Like they all prove that for SL2 and only for like punctured sphere and torus, but this is some general idea that somehow should be true at least heuristically. Is that this thing in some way is a quantization of this action by isomorphism. And I'll tell you what I mean by that. So there is a universal version of this connection in the case where you start with an elliptic curve, which is due to Karak and Enriquez-Ettinger. And what I mean by universal is that you can replace S of G by any G of G module. And in fact, they do better than that. They also encode this structure in this representation in some canonical structure on the category of DG module in such a way that you get this action on the invariant here. And they also sort of get as close as you can get from some algebraic description of this of the monodromy.
How does the S of G to the genus?
Oh, sorry. Yeah. That should be to the power of G. I was already thinking of that elliptic curve. Yeah. Anyway, And the idea here is that so there is this action of the braid group, which, because of the Riemann-Hilbert correspondence, sort of preserves the symplectic structure on there, because if you have a one puncture, like an elliptic curve is a one puncture torus, so the moduli space of flat connection is a question of that. And the Veil algebra, so differential operator little g, is a quantization of this symplectic structure. And so the sort of vague claim somehow is that this braid group action you get for d of g instead of t star g is a quantization of this action by isomorphism. And some almost theorem, or at least some work in progress, is that actually there is some lift of the construction by Kalak and Riemann-Hilbert. So there is some algebra in the KZ version of this representation category of G, which actually its module in this category are the same as just G equivalent module for that. So somehow you change the algebra, but you don't change the category. And I claim that there is some natural way to define an action of the elliptic braid group on that category, and that if you take invariant, then you recover the formula from Kalak-Henry-Kazetinov. So again, somehow I claim that Kalak-Henry-Kazetinov is some sort of the affine version of something that has a sort of stacky lift, and that this one will somehow behave better. And then the main claim is that there is actually a formal equivalent, by which I mean equivalence upon completion of the algebra on both sides, between this category on factorization homology of the puncture torus, and that this equivalent is, I expect, valid. It's close to have a proof that it actually intertwines the action of the elliptic braid group. And I'm actually early. So that's nice. Thank you for me. Thank you.
Any additional questions, comments?
Before real questions come, can you just back up the slide? Sure. Put the last slide up.
So I guess we already knew that rep QG and rep K set G were equivalent in very modal categories. So one could just pull back this DQG through the equivalence to some object there. Is that how you define D twiddle, or is it actually something else, and then you need to check that it's the same as this?
That's actually something else. In a way, so I'm mentioning that there are, in a way, there's some sort of like combinatorial or finite dimensional version of this Riemann-Hilbert Poisson version correspondence, which is due to Alexeyev, Malkin, and Meinrich. And the way they do that is basically they have some recipe that tells you that if you start with some Poisson structure with a moment map in the classical sense, there is some standard way of like turning it into what they call a quasi-Poisson structure with a multiplicative moment map in such a way that if you mod out by G on both sides, you get the same Poisson structure. And then this one in turn is equivalent to the Atiyah Bott structure. And somehow what I have is a quantization of this process. So this lift I was talking about is like the first step. You start from an algebra in rep G, and you deform it, like you lift it to an algebra in rep KZ G, and I claim that this is a quantization of this AMM construction. And then after that you have to identify the
Such lift unique?
I
mean, can it be characterized by its properties?
yeah, I mean, there is, let's say there is a sort of natural construction. Like I didn't say the word, and I really had to find it because that's my favorite thing in life. This rep KZ category is described using something called Drinfeld associator, which is one of my favorite things. And there is some, so basically you start with rep G and you plug a Drinfeld associator and you get rep KZ, and this is some really automatic thing. And there is basically there is an analog construction. If you have an algebra with an algebra map from UG, you can sort of map the associator to A tensor UG, and somehow this does give you a deformation of the category of A module, sort of automatically. And then you have some abstract nonsense that tells you that it has to be module for an algebra. In fact, you can check that it's some, I want to say some quasi-op version of the adjoint action, if you know about quasi-op algebra.
Elliptic braid action comes for free.
Like here, this is really just some construction that take an algebra with an algebra map from UG and turn it into an algebra in rep KZG. And then if you do that for DG, And in general, you will get some action of the bread group of the annulus, because you get some categorical structures that we are using a lot, which are called bread module categories. And it turns out that if you do that for DG, you have like 2 of those, and they are compatible, and we get this action of the elliptic bread group. That's a very, very short version.
And sorry, when you said the Riemann-Hilbert correspondence, you didn't mean that it is an isomorphism.
What that was an isomorphism.
You have, on the left you have local systems, and on the right you have multimodal. It's not really subjective in this way. But on the open side.
I think
You had regularity.
I think the Starkey version are actually isomorphism. Analytically, but I'm really working formally, so I must admit I don't really know sort of global details, but I think that's kind of one of the point of using stack is that somehow it sort of solves those kind of problems for you. But I'm not very sure. Say again? I don't know. Even at the level of classical stack, I feel that my approach. I'm looking at something else. If he doesn't know, then I'm typeless.
Other questions?
So for hygiene, do you expect like a mapping class group actually?
Oh, thank you. Yeah, I should have mentioned that. So in fact, I talked about the bread group because that's easier, but somehow is almost another thing. You can also like change the complex structure, so the tau parameter in that case. And I sort of expect to have equivalence with the mapping class group action, but the sort of C version of that is already pretty complicated. Then as far as higher genus is concerned, somehow the proof doesn't really use anything special about genus 1. The sort of only problem is that there is no analog of CBE in that case. And if you have a look at their paper, you'll see that that's not a trigger test to do that.
So but for about hygiene, there is also this algebras of Shakirov and Koester for the genus 2. Is it related to the algebra?
I really don't know anything about that.
All right, let's thank Adrien again. And since we're on time, we come back at 11:40.